Okay, our next speaker is remote. I'm pleased to introduce Claire Jang from McGill University, who's going to tell us about metaprogramming using contextual types.
Hello. Hello, I'm Junyoung Jang and gonna present the paper Moebius metaprogramming using contextual type, the stage where system app can pattern match on itself, which is a collaborative work with Samuel Gélineau, Stefan Monnier, and Brigitte Pientka. Let's start with this question. What is metaprogramming? Metaprogramming is the art of generating, manipulating, and analyzing code. This technique is nearly universal. Compilers, user libraries, and program analyzers use this technique. For example, the standard library of Rust, Django framework of Python, and Metacook project are a few concrete applications. However, metaprogramming systems have been suffering from one issue. It is hard to write a reliable and safe metaprogram. One reason for this difficulty is a tension between features and type safeties of metaprogramming systems. There have been several approaches to provide a type-safe metaprogramming system with powerful features such as open code fragment and effect. Tao and Shield, as well as Tao and Nielsen, provided type system for pure functional metaprogramming from a practical point of view. Kisalov et al. Suggested an ML-based system that can handle side effects as well. On the other hand, Davis and Fanning and Nanevsky et al. Provided a logical foundation for metaprogramming based on the box modality. Following these lines of works, we introduced Moebius, a type-safe logical foundation which logically handles the following metaprogramming features: the generation of system app-style polymorphic code, generation of code depending on code and type templates, and pattern matching on code and type. Built on the contextual model lambda-calculus of Nanevsky et al., which supports open code fragments, our foundation, Moebius, as type variables, multi-levels, and pattern matching on code and types. Also, we show that our foundation satisfies the type preservation. In this talk, I'll demonstrate how our foundation deals with each feature. Before diving into our foundation, I'll first show how the contextual model lambda-calculus, which Moebius is based on, works. The contextual model lambda-calculus uses a contextual type to characterize an open code fragment. It consists of two parts: the context, where a code fragment can be type checked, and the result type of the generated code fragment. The typing judgment in the calculus uses two contexts separated by a semicolon: the global context delta, which is accessible in any future stage, and local context phi, which is accessible only in the current stage. It checks whether a term E has a type T in those contexts. The calculus has three main typing rules: introduction of a code fragment, elimination of a code fragment, and a rule for contextual variable. For the introduction of a code fragment, box psi E, we check the code E inside its local context psi instead of the current local context phi, while keeping the global context delta as is. When you eliminate a code fragment with left box psi U equal E1 in E2, we first stage the code fragment E1 as a contextual variable U to the global context delta, and type check the body E2 in the global context extended with U. Finally, when we have a contextual variable U in the global context delta, we can bring it to the current world with the substitution sigma from its local context psi to the current context delta phi. Now let's dive into Moebius, a multi-level polymorphic extension of this calculus. Our foundation first extends this contextual model lambda-calculus with system F-style type variables to generate a polymorphic code fragment. Here we use the function s that generates a code fragment to access nth element of a RISC-V. In this example, the steering here means that the function s returns a code fragment. This prime a colon star in the context is our extension, which allows the return result code fragment to depend on the type variable prime a. The entire return type means that we should provide the RISC-V and, more importantly, a type prime a in order to execute or splice in the return code fragment. When you have a code fragment, for example, in this case, obtained by recursively calling n's on n-1, we can use letbox to make code available in the current and future stage. Here, X stands for an open code template which may contain type variable prime A and a pre-term variable V. Once we have a staged code template X, we can instantiate it with using with. In this example, we substitute this violet prime A found in line 6 for the free type variable prime A in X, and the tail of the violet V for the free term variable V in X. When you call nth with an integer 10, it will give us a code fragment that applies head to a RISC-V after 10 applications of tails. Since a programmer can choose the type prime A after the generation of this code fragment is polymorphic. Also note that thanks to the contextual type, this result does not contain any redundant lattices like a lambda abstraction immediately followed by an application. Moebius also allows a code fragment to depend on code template unlike prior works. Here we have an example of constructing an arithmetic expression by composing two code fragments using this feature. In this example, we have a free variable c to which we can apply a substitution directly without any letbox. We refer to such c, it asked what it can obtain after staging a code fragment as a code template. If we want to use a code template u, which itself contains a free code template variable c, we should provide the substitution with some code template. Here we use R for that. By replacing the free variable c and x with R and Z, we get this intermediate code with the remaining instantiation for R, and again by applying the substitution of 2 times Z to R, we get this result code. Note that this result code does not contain any undesired lattices. In prior works, where code cannot depend on a code template, we need to write this. This generated code fragment has this undesired lattice, a box followed by a letbox. The direct dependence on code templates, as shown in this result, allows us to avoid this kind of undesired lattices and to produce a true arithmetic expression. Avoiding these undesired lattices, lambda after applications, lambda followed by applications, and box followed by letbox, is itself important for the usability, but becomes even more crucial since we support pattern matching. This is because if we had such lattices, they would change the branch with which a code fragment matches. These features lead us to extend the 2-level contextual model lambda-calculus to multi-level polymorphic calculus. In the 2-level calculus, there are 2 contexts, the local context phi whose entry does not have any local dependency, and delta, whose entry can depend on its local context. However, this local context of an entry of delta cannot contain any code templates. It asks anything that can only go into delta cannot go into local context. We generalize this structure so that there is a context whose entry can depend on such a thing that can only go into delta. Here, the first two, gamma 0 and gamma 1, are just renamed phi and delta of the two-level calculus. After then, just as an entry of gamma 1 can have a local context of level 1, which is something like previous psi, an entry of gamma 2 can have a local context of a level at most 2. Likewise, gamma 3 can have a local context of a level at most 3, and so on and so forth. With this extended context, we can also generalize the typing rules of the two-level calculus. These are the typing rules of the two-level calculus, which I showed in the previous slide 6. To generalize the two-level introduction rule, we generalize these two contexts into our general multi-level context. We also add an explicit level n for the local context psi to facilitate the type checking. Next, instead of keeping the entry in delta as in the two-level calculus, we keep the entries with the level greater or equal to n. In other words, instead of replacing only level 1 context phi with psi, when you check the code E, we replace anything below level n in gamma with psi. Here, this bar subscript n means that we want the context but without any entries at level less than n. For the elimination rule, we also generalize these two context parts n as explicit level n. The part where we really need to generalize is the context into which u is inserted. In the two-level calculus, u always goes into delta. In our multi-level context, we insert u into the place where all the level n entries are posed. Here, this circle plus means inserting u to the right place for level n entries. We also extend this multi-level modal lambda calculus with pattern matching on code. This requires two main tasks. First, we need to characterize pattern variables. And second, we need to refine type variables during pattern matching. First, I'll describe how we can characterize pattern variables using multi-level contextual types. Suppose that we pattern match on the code fragment above against the pattern below, which has a pattern variable p. Just as the function body in the scrutiny refers to x, a variable bound in the code, a code template for p should also be able to refer x. In the case of lambda abstraction, we can use the two-level contextual type to describe this dependency. However, the two-level calculus cannot handle all the patterns. When we pattern match on a code fragment against a pattern using labbox, we need to characterize a pattern variable like this q. Since it is possible for this part of the scrutiny to depend on x, the type of q should also allow this possibility. This dependency on x cannot be described in the two-level calculus. This is where a level comes into play in terms of pattern matching. In our multi-level calculus, we can describe the type of Q as a level 2 contextual code template, which itself depends on a level 1 contextual code template, X. Along with the characterization of pattern variables, we also need type refinements because our calculus allows polymorphic code fragments. Suppose that we have these code fragments whose type uses a type variable prime A and matches on it against the pattern below for an integer code. By matching the type of the scrutiny and pattern, we know that prime A should be int in the branch by the standard unification. Thus, we need to generate a constraint like this on prime A, as we do with GADTs, index types, or dependent types. As we want to check types modulo this kind of constraint, we extend our context to track constraint from type refinements. In short, Moebius is a type-safe logical foundation for multi-stage programming that can handle, first, polymorphic code based on code depending on type variables, and second, code depending on code template based on code depending on level greater than 1 variables, and finally, pattern matching on code based on the characterization of pattern variables using labels and type refinements and the tracking of the constraint. For the future, we will explore how to implement program optimizers in this framework and extend the system to a logical foundation for multi-stage programming with dependent types to exploit the full potential of typed metaprogramming. If you want to see more details of our foundation, please check our paper. Thank you for listening.
Okay, we have time for some questions. Okay, I have a question.
Okay.
So it looked like when you were, sorry, can you hear?
Yes, I can hear you.
Okay, so it looked like you were doing pattern matching on type variables in the context.
Yeah.
Which would allow you to match them against concrete types. Is there a way to, or maybe even a reason to enforce that type variables be treated parametrically to kind of prevent?
If you put the type variable itself in the context, then it will become it's invalid to pattern match against such a type variable because such a type variable should be treated as parametrically. However, if you bound the type variable outside of the function, I mean, if you have top-level definition that depends on that is itself polymorphic, and if you do the pattern match inside of the function, then the pattern matching should allows you to have a more refined type in each branch. So it's really like how we deal with GADT or index type, dependent types, those cases. Like if you have a polymorphic variable itself inside the code fragment, then it's invalid. But if the code type variable comes from somewhere outside, then the pattern matching should give some constraint on the variable.
So if I understand you correctly, you can use parametricity from the sort of meta level to enforce parametricity in the object level?
No, I mean they are separated. Like so, in my example, in my example here, if prime A is not bound inside of the context, they are outside, they bound outside from, they come from outside of this code fragment. However, in like this ANSI example, in this ANSI example, prime A is served in the context. So it is like polymorphically bound in the for the code fragment, and you cannot pattern match on that prime A to create some constraint, because that prime A will be chosen after the generation.
Okay, thank you. So we have some questions online. So the next question is, have you considered multi-level contextual diamond modality?
Actually, no. The honest question is no. Honest answer is no, because we haven't considered diamond modality. The ultimate goal is more like going to the direction of dependent type with metaprogramming with dependent type. So like we are focusing on the contextual box modality instead of considering diamond modality.
I will confess I don't understand the interpretation of diamond modality here. What does it mean to you?
For me, diamond modality means the possibility modality. It is possible, where the box modality means it is necessary. That's my understanding for the diamond modality.
Okay, so one last question. Does matching on code affect the equational theory of code at higher stages?
It can. I'm right now. I'm not sure about that. Okay.
Okay, so we are out of time, but thank you once again for a lovely talk.